All right, here we go. So today we're going to talk about the basics of probability. So what we have done the past couple days is we have talked about how many possible outcomes there are. We haven't talked about probability. What we've done is we've basically been learning how do you calculate the denominator for what we're going to do. So the probability is the chance that an event will occur out of all possible events that can occur. So maybe yesterday we were talking about how many different outcomes are there when you flip a coin. So when you flip a coin, how many possible outcomes are there? 2. Now, today we're going to say, okay, what's the probability that I flip a coin and it lands on heads? So how many heads are on there? Just 1. So therefore, the probability would be 1/2. So your sample space is what we've been doing. This is all the possible events that can occur. So in the coin problem, your sample space would be like heads, tails. An event is a single outcome within the sample space. That W/I, that stands for within. So maybe the event I'm talking about is a heads. What is the possibility that a heads comes up? The probability of an event we write as, it kind of looks like a function, P and then parentheses E. So the probability of an event happening is the size of the event divided by the size of the sample space. So if I said, what is the probability that I flip a coin and it comes up heads? So the size of the event, so there's only one way it can come up heads. The size of the sample space, so there's a heads and a tails, is 2. So I know I overcomplicated that, but sometimes the problems do get more complicated. But that is your reference. So the probability that an event will happen is a number between 0 and 1, which is the same thing as 0% to 100%. Because 0, this is a percent, you turn that into a decimal and you get 0. 100%, if you turn this percentage into a decimal, that means you're moving it 2 spaces to the left and you get 1. So these are the same thing. Today we're going to talk about independent events. An independent event means one event does not affect another event. So think of when you flip a coin and then draw a card, perhaps. How you flip the coin has zero impact on the card that you draw. So one thing has nothing to do with the next. These are independent. The other kind of event that happens is called a dependent event. This is when the outcome of the first influences the outcome of the second. This would be like, I draw a card, I don't put it back, therefore no replacement, that says no replacement. And then you draw another card. So I first started with 52 cards in the deck, and if I don't put it back, then when I draw my second card, that is influenced by my first thing that I did. So this would be an example of dependent events. All right, so we're going to first, now we're going to do the sample space. So what is the sample space for rolling a die? So if you roll a 6-sided die, what could possibly come up? You roll it, what number could come up? 6. What else could come up? Okay, so the sample space is 1, 2, 3, 4, 5, and 6. So there were 6 different things that could happen there. Now I want the sample space for flipping a coin. So you flip it, and it could come up heads, or it could come up tails. So there are 2 different things that could happen there. So what is the sample space for flipping a coin and rolling a die? So you could get a heads and then a 1, a heads and then a 2, heads and a 3, heads and a 4 on the die, heads and a 5, heads and a 6. Or you could flip it and get a tails and a 1, a tail and a 2, tail 3, tail 4, tail 5, tail 6. All right, so here is my sample space. So I have 2, 4, 6, 8, 10. I have 12 different ways that these could happen. Well, this is kind of what we did the other day when we did the fundamental counting theorem. So we took how many times one event could occur times how many times the second event can occur, and we multiplied them together. So this right here is 6 times 2 equals 12. That's the fundamental counting theorem, which I think was in like 5.1. So this says, given a standard 6-sided die, what's the probability of rolling an even number? All right, so I want an even number here. So an even number would be a 2, a 4, or a 6. All right, so I want the probability of the event. So there are 3 ways that I could get that. And then the denominator is how many different options there are. So the top one is the desired outcome, and the denominator is all the possible. So we have 6 numbers on a die, 3 of them are even. So therefore the probability of rolling an even number would be 1/2. Sometimes you're given a table of values. So this says determine the probability of selecting an employee that is between 25 and 34. Okay, 25 to 34 is what we want. So we have 366 people that are between that. So that is my numerator. That is my desired. I want out of 3, there are 366 people that are between that. But what is my denominator going to be? You got to add them all up. I'm going to speed this along today, and I'm going to tell you it's 1,000. All right, sometimes it'll want it as a fraction, sometimes it'll want it as a fully reduced fraction, sometimes a decimal, and sometimes a percent. So could you put this into your calculator and change that into a decimal next? You just go top divided by bottom. Yeah. I didn't round that properly, I don't think. I think I just truncated it and stopped it, didn't I? Because that 6 keeps going, doesn't it? Is it 0.666 repeating? Okay. All right, so maybe I'll at least round it properly. We'll call it that. What if I said I want this as a percent? Can you turn a decimal into a percent still? Okay. So if you just move it 2 to the right, that would be 36.67%. Next one says, determine the probability that you find someone between 45 and 64. So now I'm hitting 2 different groups. So what do you think I'm about ready to do with these 2 numbers? Yep. So 180 plus 125 divided by 1,000. Then I would turn that into a decimal and then turn that into a percent. So when I go top divided by bottom in my calculator, get 0.305. Turn that into a percent. I would get 30.5%. Let's see. I want no more than 44 years old. No more than 44. We want people older or younger than 44? Younger, okay. So I need that group, and that group. All right, so those are all the groups that are less than 44 years old. You're going to do the math on top. We're going to get a decimal. And we're going to turn that into a percent. All right, here we go. Determine how many different computer passwords are possible if you have 3 digits followed by 4 letters and repeats are allowed. All right, so I haven't done the probability yet, so this is like what we did the other day. I want to know how many different passwords there are. All right, so quite frankly, when it's something like this, I think drawing the little hashtags and kind of organizing myself is the best way to do it. Okay, so I have 3 digits. So in these first ones, I got number, 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 followed by 4 letters. Letter, 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 letter. And in this one, we have repeats are allowed. So, how many different digits are there? 10. So, when you count 0 to 9, there are 10 digits. Repeats are allowed, so you could have 111 if you wanted to. And now we're followed by letters. So, how many letters are in the alphabet? 26. And repeats are allowed, so you could go A if you wanted to. So this is what we did the other day. This is an independent event. And when you multiply those 7 numbers together, you should get a 9-digit number that starts with a 4. I'm going to keep this video and this lesson going. Should get 456,000. No, 100,000. 456,976,000 possible passwords. All right, so when we had repeats allowed, this was an independent event. Let's say we have almost the same scenario, but we have no repeats that are allowed. All right, so I got a password that goes number, 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 1, 2, 3, 4, followed by letter, 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 letter. So in the first one, you have all 10 digits that are available to you. But basically it says, okay, so if you used a 1, now you're not allowed to use the 1 again. So now how many number choices are you down to? 9. And then maybe use the 1 and the 2 and you aren't allowed repeat. So now you're down to 8 different choices right there. So when you start the letters, I have 26 options. And then if you're not allowed to repeat, then you're going to have to keep decreasing this number by 1. So if you multiply those 7 digits together, did you get a number that starts with a 2? Yep. All right, so I have 258,336,000 1,000 possible outcomes. So when there are no repeats allowed, this is an example of a dependent event. So the next number that I have the option of choosing is affected by the prior event. So when it says no repeats allowed, so that is what a dependent event would look like. All right, now we're going to go back and we're going to calculate some probabilities. So I have a coin and I have this spinner here. So how many numbers are on the spinner that you're looking at? So we have 6 numbers on the spinner, and on a coin I have heads and I have tails. So I have 2 options here and 6 possible outcomes on here. All right, so this says, what is the probability that you flip a coin and it lands tails, and then you spin the spinner and it lands on the 6? So that's how you read this. So first we're going to do, what is the probability that you flip a coin and it lands tails? Good. Now, what is the probability that you spin this spinner and it lands on the 6? How many 6s are on there? Just 1. So that would be 1/6. We multiply fractions straight across around here. So when you multiply across, you go 1 times 1. And you multiply across and you go 2 times 6. So the probability that you get a tail and then a 6 is 1/12. I'm going to go across, yeah, I'm doing 4. So the first one says, what's the probability that you get heads when you flip the coin? So that would be 1/2. And now you're looking at the spinner. A probability that it is less than 4. So how many numbers are less than 4 on the spinner? Thank you. You either need to reduce now or you need to reduce at the very end, but at some point you need to reduce. Or, quite frankly, you could put it into your calculator if you wanted. So the ABC button would be good for this one. So you could go 1 ABC2 times 3 ABC6, and it'll automatically reduce it for you. And if you use your calculator, you should get 1/4. You guys are doing 5 and 6, and I'm going to help the kids in class, and we'll be back. All right, so the probability that it lands on the heads is 1/2. The probability that it lands on an even number, so I have a 2, a 4, and a 6. So I have 3 out of 6 numbers that are even. When you multiply straight across, you get 3/12. I simplified that and I divided the top and bottom each by 3. And that's how I got 1/4 for a fully reduced answer on that one. Probability that it lands on heads is 1/2. And the probability that it is less than 7. So there is a 100% chance because all those numbers are less than 7. So maybe you write it as 6 out of 6. Well, 6 divided by 6 is the same thing as 1. and a half times 1 is 1/2. So there is a 50% chance that, that basically you're going to flip a coin and get heads. All right, so the name of the game is if you have independent events, you're going to calculate each and multiply them together. That is the gist of what we're doing here. When you have independent events, you calculate the probability of each event and then you multiply it together. I have a fair 14-sided die with numbers 1 to 14 with a different number appearing on each one. If the die is rolled one time, what is the probability that I roll a 2? How many 2s are on the die? 1. How many, what's the denominator? How many possible outcomes? 14. Yep. Sometimes there's no work to do, it's just read it and interpret it. All right, I got marbles in a bag. One marble is randomly selected. If the probability that the red marble will be selected is 5/8, how many red marbles are in the bag? Oh, we got to do math. Cool. All right, the probability that a red one is 5/8. That means that for every 8 marbles in the bag, that 5 of them are red. So this fraction right here, if you kind of write it down, it's saying it's a ratio of the number of red to the total number of marbles. So the given ratio here is 5/8. So I labeled it, so now all my reds are going to be in the numerator and all my totals are going to be in the denominator. Because it says there are 1,096 marbles in the bag. So in my next fraction, I have 1,096 marbles. Therefore, how many are red? So that is your variable, that is your unknown. I got fraction equals fraction. We can do this. How do you do fraction equals fraction? Cross multiply. 8 times x is 8x. 5 times 1,096. Should be 5480. Just do a little bit more algebra. Divide both sides by 8 to solve. And you should get 685 red marbles. I'll do 9 in a minute. Number 10, I have 6 green socks, 4 blue socks, 2 red socks. What's the probability that you randomly select a blue sock? So I want the probability of drawing a blue sock. So when you write it, you want your favorable, which is blue, to your total or all possible options. So how many blue socks do you have in the drawer? 4. How many socks do you have altogether in the drawer? Okay. What is the probability I think on the test or the quiz, I will tell you how I want your final answer, whether I want it as a fully simplified fraction or a decimal. What is this as a fully simplified fraction? Good. We have the probability of something not occurring. We have the same socks in the drawer. What is the probability you do not select a blue sock? All right, so there are two different ways that you can do it. Option A is what? I'm going to hit pause and they're going to think on that one. All right, so the one way that occurred to them was figuring up how many red and green. So what's the other option so that you don't draw a blue sock? And so there were a total of 8 red and green, and there are still 12 socks in the drawer, and that reduced down to 2/3. The probability of something not occurring is 1 minus the probability that it does occur. So the chance of you drawing a sock is 100%, which is 1 as a decimal. And so the probability of something not occurring would be 1 minus the probability that it does, which is 1/3 in this case. And 1 minus 1/3 is 2/3. So you get the same answer either way. If you've already done the problem, then this might occur to you. If this doesn't occur to you, then you could do it the first way. In the next section, we are going to have dependent events. So for the dependent events, each time you remove a marble, you're not going to put it back. So dependent probability means that one event is affected by the other one. So this is going to happen when it says you draw something without replacement. So you draw one and you don't put it back. All right, so the first thing that you should do is you should count up how many red, blue, green marbles there are and figure up the total, and then I will start the lesson. All right, so they calculated and found that there's 4 red, 7 blue, 5 green, and 16 total marbles. So this is the format when it wants you to calculate the probability. So we want the probability that I draw a red marble followed by the probability I draw a green marble. So the probability that you draw a red one first is what? Okay. Now you want the probability you draw a green marble. But that red one that you drew, you aren't putting back in the jar. So now how many marbles are left in the jar? Okay, so what that does is that when it says without replacement, your denominator is going to go down 1. So how many green marbles are there? Okay. I think this is an instance where I would probably just use my calculator. The ABC button is great for this one. I would probably go 4 ABC 16 times 5 ABC 15 equals, and that will give you a fully reduced fraction answer. What'd you get? 1/12. 13 says I'm going to draw, what's the probability that I draw a red and then another red? So what's the probability that you draw a red one? Okay. I didn't put it back. I didn't put either of them back. So what's the probability that you draw a red one again? So how many reds are left in there? 3. And how many total marbles are left? 15. Multiply that together, and bell's going to ring. You should get 1/20th, and we will talk about cards tomorrow. Thank you. All right, to finish this up, so the probability that I draw a green one, so there are 5 out of 16 greens. And then probability of drawing another green, so now there are only 4 left in the jar, and there are only 15 marbles left in the jar. And when I multiplied that, my calculator reduced it, and I got 1/12. Probability of drawing a green is 5/16. A blue, 7/15. Another blue, so that one reduces to 6. And now my denominator reduces to 14. And so that probability is 1/16. Okay, so now we have cards. So in a standard deck of cards, there are 52. We have 4 suits. So a suit is whether it's a heart, a diamond, a club. Let's see. Hold on. All right, so we have clubs, spades, and we have hearts. There's another spade. And then we have diamonds. So we have 4 different suits. And so if I kept laying all of them out and organizing them, there would be 13 of these. So there's ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king of each suit. So there are 13 clubs, 13 spades, 13 hearts, and 13 diamonds. Okay. So it says, what is the probability of drawing a heart? All right, so I have the probability of a heart and then a spade from a standard deck of 52 cards. Assume they are not replaced. All right, so just explain that there are 13 cards of each suit, so there are 13 hearts out of 52. And then you draw spades, so there are 13 spades, and now there are only 51 cards left in the deck. And when I multiplied that, the probability is 13 out of 204 that you draw a heart and then a spade. Next one says, what is the probability of drawing a 3, then a red 5? Assume that they are not replaced. All right, so when I had the cards out earlier, so I have the 3 of diamonds, 3 of clubs, 3 of hearts, and somewhere in here there should be the 3 of spades, wherever it's hiding. So there are 4 different 3s in the deck. So the probability of drawing a 3 is 4 out of 52. Then I want the probability of drawing a red 5. So in the red cards, there are hearts and there are diamonds. So there are actually 2 red 5s in the deck of cards. And now there are only 51 cards left because it says that they are not replaced. And when I multiplied and reduced, I got 2 out of 663 for a good final answer on that one.